Well, I think it's time to begin. I'm gonna give a presentation of the OpenBSD remote exploit. My name is Alfredo Ortega. I work as exploit writer for core security. Sorry about my pronunciation. This time of the morning is a little unnatural for me to be awake for. So let's start. Please, nobody hack my machine while I'm doing the presentation. Thank you. Okay, this presentation is about how we found and exploit a bug in the OpenBSD operating system. The OpenBSD operating system is a very secure operating system. It only has two remote exploits, GNU or public, and I'm gonna try to explain how we found bugs, how we found this bug, and how we exploited it. Okay, let's start. First, we're gonna speak how I found this bug. My boss gave me an assignment a few months ago to research a known patched bug of OpenBSD. It was listed as a reliability fix, and we really didn't know much about it, so we must start research on how to reproduce it. In fact, it was a denial of service. It was not exploitable, so we started to try to reproduce, to craft an attack for this exploit, for this bug, sorry. So the bug, in fact, was an infinite loop in the kernel. An infinite loop caused the kernel to stop working, and every process in the operating system stopped working too. So it really was very much info. You can see about it. I started to write a program called, like you know, a fuzzer. A fuzzer is a little program to send malformed data through the system to try to break it. It was a very primitive fuzzer. Let's see here. It was a very primitive fuzzer. It was almost manual fuzzer. Its purpose was to craft a couple of packets and to send it to the system. We know that the bug was in the ICMP protocol, so the fuzzer was sending malformed ICMP packets. But in a couple of days, the fuzzer started to break the system. I was thinking that I was found the failure. It was in fragmented ICMP packets, and when we sent the packet to the OpenBSD system, the system just broke apart, just crashed, and I say, well, look at me, I found the bug. The bug was not an infinite loop like it was listed in the website. So it was very strange. It doesn't seem the same bug, it seems another bug. This is very common when you are developing an exploit. You almost a lot of time you find a new vulnerability because you are trying to break the system to find an exploit if there is not much info. So the system was crashing, and I say, okay, I found the bug. I download a new copy of OpenBSD, the fresh copy, the patched, and test the attack against the new OpenBSD kernel, the latest OpenBSD kernel. And the exploit was working. So I say, how is this? The OpenBSD kernel was patched, and the exploit was working anyway. So this was a new vulnerability. We really didn't know what kind of vulnerability was this. Was a denial of service, or this was exploitable. We just listed as possible exploitable vulnerability. In the start, we only get a denial of service. We send a couple of packets, and the OpenBSD crashed in a new way. every OpenBSD kernel crashed in this way. We say, okay, we got a new vulnerability. We reported it to OpenBSD, and the OpenBSD team say, it's okay, it's a new vulnerability, we're going to patch it, and they patched it, it's okay. I must say that I really don't know, I am not an expert on the OpenBSD kernel, I'm just an expert writer. Maybe some from the OpenBSD team know a lot better than I the memory structures and the internal functioning of the OpenBSD kernel. So, so this time we got a new denial of service. I was patched in a couple of days, and it's okay. We started researching if this was exploitable or not, because I was thinking that this was really exploitable. OpenBSD team was saying that it really was not exploitable. So, what is the reason that the OpenBSD kernel crashed? It was because of a buffer overflow. In the kernel, we got these structures named mbuffs that are used to store network packets. It's a very common structure used in a lot of Unix systems. So I send two packets, and one of the fragmented packet overflowed these structures. We can see here one packet should fit in just one of these structures. But the packet was overflowing and was writing all over the buffers. These buffers are implemented in a linked list. So if we overwrite all the linked list, when the OpenBSD kernel was trying to process that linked list in any way, it crashed because the header of these packets were overflowed with garbage, with data that I was sending to it. It crashes in a lot of ways, but one of the ways that it crashed was in this function that is called here, the m3m function. When the operating system crashes, it shows a stack trace of the crash, where it crashed, how it crashed, and much of the time, this function was crashing. The m3m function is a function used to free these buffers. So I say, it is strange, it's crashed in a free function. In a lot of exploit, when you got a system that crashes in a free function, it's a very positive signal that the bug is exploitable, because this function does what we call an unlink of the buffers. These buffers are, as I was saying, in a linked list. This function free one of these buffers and exchange some pointers to make one of the buffers available again, but these pointers that are linked to these buffers are being overflowed. So the function crashed. And I started to research on this function to see if I can exploit it. Here. The OpenBSD kernel is open source, and I really got the C source, the source code of the kernel, but I am more used to see in this way, to see the disassembly of the functions. This is a disassembly of the function that was crashing, the m3m function. Like we can see here, m3m, this function was crashed. Oh. Where was crashing? Was crashing in the block marked with yellow. We can see here that this was crashing here. This is the beginning of the function, and the function was advancing. Sometime we reached this block and we crashed exactly here. So I started to research why it was crashing there. Because this is making some operation with pointers. Here we can see that the ESI register, what this is, I'm gonna to clarify this. This is in Pentium and 32 bits. All this exploit was researched in a 32-bit machine, Pentium. OpenBSD run in a lot of machines, but this research was only in 32 bits. So we can see this is 32-bit assembly. We can see here that the function first is used to free a block. The block is put in the AEC register. A pointer to the buffer is placed in the AC register. So then everything that is referred to this register is in fact referring to the buffer. So here is exchange two pointers of this buffer are moving a pointer with this buffer into a register and then exchange it with another. This is called a run link. This is, with this operation, we free a buffer of the linked list. And because of this pointer was being overwriting, this function in fact was trying to writing in any place, in a place in the memory that did not exist. So it caused a fault and the kernel was stopping. I was trying to reach this function. I say, this is commonly exploitable with an operation that is called 4-byte copy. With this operation, we can send in specially crafted pointers here, and because we can control these pointers, we can cause a 4-byte write everywhere in the memory. We can write a value that we control in every place in the memory that we want. It's a commonly technique named mirror write or a 4-byte write. It's used in user mode. This time it's in kernel mode, but it's the same instruction. I was trying to reach this block with controller data so I can exploit it. And then, after a lot of work, I realized that a little at the side, let's say, of this function was another couple of instructions that are doing a little strange thing. First, it copies some pointer from the buffer, from the buffer that I was sending, to a register, EAX register, and then we can see the arrows here. Does some things, it does some things, and then call to this register. First, copy from the buffer to the register, and then call this register directly. But this register was controlled by us because we are sending the data here, and then the system is calling our data. So we can modify the execution pointer of the kernel. We can make the kernel to jump wherever we want it to. Very easily, we only must place a pointer in this position of the buffer. We remember that the AC register was pointing to our packet. So in the packet, we put the pointer, and the system jumped to our pointer. That's simply as that. It's simply. And much easier than this way of exploit the system. This way, we can write anything on the memory, but really we didn't know where to write or what to write. But using this couple of instructions here, we can make the system jump wherever we want with a simple pointer. So I was trying to reach these instructions. It was a little difficult, but it was. On the end, I made it. We can see here the source code where it is calling. This is the source code. This is assembly compiled form, and this is the source code. We can see that the source code is a little difficult to understand because it has a lot of macro expansion. We can see that the function here is making in red. The system compares if a pointer in the buffer exists, it simply calls it here. If the pointer is not null, it simply references it and jump. Because why the system is doing it, is doing that. It's a very common, very common way to manage memory buffers. that it needs its own memory manager, and so in the same buffer, the structure, the header, got a pointer to a destructor, to a function used to free that buffer. It's used in a lot of places. In the Samba system, is a very similar structure. I don't know what protocol used this instruction, but there are, so I used it, and the exploit worked. I send a packet here, the system got us a pointer for the packet and jumped to it. So really, we jump wherever we want. It's not so easy, because where we jump. Well, here in this picture, we can see how the packet is sent. Here are the buffers in the memory. The buffers are consecutive in the memory. Every buffer, every mbuff, got a header that says a lot of things, says where is the next buffer, the type of the buffer, and inside this header is this pointer that say if the buffer has a custom destroying function. So we overflow from here on, and only we must place a trampoline. Trampoline is called a pointer where we want to jump. We place this pointer exactly in the position of this pointer here. It's always null, but we can control it, so we put a non-null value where we want to jump, and the system only jumps to it. We can see that, well, maybe it's a little small. We can see that there are the couple of packets I need to send. The packet was a fragmented packet because OpenBSD system get confused with fragmented ICMP packet. The packet must be valid because the packet must be processed by the system. And here are the header of the ICMP packet. A little lower, they are the pointer to our function to jump. And here is the payload of the shellcode, because we know we can jump every place in the memory, but we really need to jump to our code, because it doesn't matter if we jump to the same OpenBSD kernel or another place in the memory. We're crashing the kernel. We need to jump to our code to execute our code and compromise the system and make the system do what we want. We must place our code someplace in the memory to jump to it. So it's a little difficult to find where the shellcode is placed in the memory. So we simply place next to the trampoline. We put our code. So the code is placed in the next mbuff. We now jump to a place in the memory, and next in the buffers are placed our shellcode. Our shellcode got malicious code or code that we want to execute. So we really didn't know where we are, because the mbuff, the buffers, are in a position of the memory that we really didn't know where they are, because there are thousands of these buffers. They are constantly changing the position, so we must find where our code is placed, because it can be placed in a lot of position of the memory. How we find this? How we find where our code is placed? We need to find where our code is placed to jump to it, because if we jump to another place, the system crashes. This is what's called a one-shot exploit. If we jump to a place that is not exactly the location of our shellcode, the system will crash and the exploit will fail. We must jump. We got only one chance to jump to the position of the shellcode. I was saying before that the buffer was in the ESID register. So we know that our code is in this position of the memory. We don't know where it is, but we know that the buffer is placed in this register, and then we jump to every place. So how we jump to our shellcode? We must find special instruction in all the kernel that jump to the ASE register, because we know that the ASE, maybe I say something in Spanish. We know that the ASE register got the position of our code. We only must find in the world memory, the whole memory of the kernel, an instruction to jump to the ASE register, to the ASE register. This instruction is very easy to find because it's a simple instruction. It's placed thousands of times in the kernel. So we simply find where is this instruction. It's in a lot of times of the kernel, in a lot of places of the kernel, it's used a lot. So we jump to this instruction, and this instruction we bounce to our code. We jump to the ASE jump code, and the code we back to exactly where our code is located. There are a little problem with this, is that we must jump to exactly the place where this instruction is placed, and this place might change for version to version of the OpenBSD kernel. Maybe a kernel, the instruction is placed in, I don't know, a direction, and then we recompile the kernel, and this instruction, it changed a little bit, changed maybe 1 byte. But if this instruction changed 1 byte, we want to jump to nowhere, and the kernel will crash. So we must find an instruction, a jump ASE or call ASED, call ASE, that is placed in the same position in all the kernels. It's a little difficult to find, but there are instructions that are placed in the same position. In the first part of the kernel, it's changed very little because all the change of the kernel I made, and the kernel, when you recompile the kernel, it really didn't change the first byte of the kernel. So we must jump an instruction that is placed in the first part of the kernel, and it will work the majority of the time. So we are jumping to this instruction. We are on our shellcode. We got here, got in the drawing. We know that this is all the kernel memory. We really don't know where we are, but we know that the ASE register is pointed to our shellcode. So we must jump to this place, and there is another problem. This exploit adds a lot of problems. It's very difficult. That is because we are executing it in kernel mode. It's not like another exploit or another similar programs that are executing in user mode. But when we are executing in kernel mode, there are a lot of functions that we cannot do. We cannot simply access the hard disk. We cannot access the network. A lot of things we cannot do because we need the kernel for that, and we are in the kernel. If a user mode exploit simply makes system calls or make interruption. In Unix, the interruption used is the int interruption 80. To open a file, we just call the kernel. We say, hey, kernel, open this file. Or kernel, open this connection to the internet. But we are in the kernel, and in a kernel, but that we don't know what kernel is. Maybe it's the OpenBSD 4 or OpenBSD 3 kernel, 3.8 or 3.9. So we can't use the kernel function. We must do everything in the shellcode, like if we were a little operative system. So we must place our shellcode in user mode, because in kernel mode we can't do anything. We must find a way to place a little code in user mode, because it's much easier to exploit this way. So let's find a way to place our code in user mode. How we did it? Well, on one of the few things that we could do in kernel mode is to hook interruption. We can hook hardware interruption or software interruption, because it's very easy on the Pentium processor to find the interruption table. It's only a couple of instructions. So we say, well, what if we hook the system call? What if we hook the interruption 80? So every user process gonna call when every user process will make a system call. In fact, they are calling us because we hooked this interruption. Like in the old DOS terminate and state resident program, in like 10 years ago, there were a kind of program that hooked the timer function, and this way they remain in memory. Well, we do exactly the same. We hook the system call. We first found the interruption table in memory, and then we say, no, now the interruption 80 is us, and the shellcode, or us, call the kernel, and the kernel returns. But it's like a man in the middle. We are in the middle of every system call. You can see in this drawing, first the normal system call, make a int 80 and call the kernel, and the kernel returns to the user process. But we are made a hook, and the system, or the user process, call all code, and all code call the kernel. So we are intercepting every system call now. So we are gaining a little more information. We now can intercept every system call of every process. This, of course, makes the system a little slow because we are processing, we are injecting code in every system call. There are thousands of system calls per second in a running system. So here are hooking every process. In this way, we can override. By example, we know that some process is calling us, and we can override the return pointer to this process, so we can make the process we can make the kernel to return to every place of the process. But we really need a process. We really need a process that got administrator privilege, that got high privilege, because we are now intercepting every process. The printing process, the send mail, Apache server, and we need a process that got a lot of privilege, got a root privilege, because if we intercept a process that really didn't have privilege, the exploit is of low value because we really couldn't do anything. So we must find if the process calling us is a root or is not. This is not simply because, as we are saying, we are still in the kernel mode. We are still executing in ring 0 here. We must find if the process calling us is root. So how we find this? We can ask the kernel, we can make a system call, get process ID. It's a common system call, but we really cannot call this in OpenBSD because we didn't know where it is. We cannot, if we are in the interruption 80, we cannot call the interruption 80. Or maybe we can, but we didn't realize how we could make a reentrant or interruption.
Just call the previous interrupt back. Call the previous interrupt back. You want to override.
Yes, I tried that, but when we call the previous interrupt vector, the OpenBSD kernel just crashed. Just say that the stack is bad, and in fact crashes in a weird way. In a little weird way, it was saying that the interruption was a kind of a Linux interruption. I crashed it. I tried a lot. I tried trying to fix the stack to make the OpenBSD kernel thinks that is a common interruption, but it didn't not work. I'm trying to jump directly to the get process ID function. That did not work either. In fact, I was saying maybe it's a way to do it. Maybe it was some little part that I was missing, but really could not make it work. Couldn't call directly a system call in the kernel. And in fact, it's a much easier way to do it. I really don't need to call this particular system call because we can read the process directly from the memory. I would like to to know how call a system call from inside a system call. That will make this exploit a lot easier. So, how we must find the process ID. So, first we must find the process ID is a memory structure is in somewhere in the memory, somewhere. Yes. I'm sorry.
How do you prevent, because you're basically using a buffer, an mBuff, to host the interrupt handler
Yes.
for the interrupt?
Exactly.
How do you prevent the system to free in that mBuff that you're using and to be reused and be never written with your data?
Yes, it's because we are doing this very. That's a nice question. I was saving that for the end, but. Okay, no, it's no problem. This happened a lot faster. The system really don't have time to free that buffer. And in my experience, the buffer can be allocated a lot of times in memory. This happens in a couple of microseconds, and the buffer can be for hours in memory unallocated. In my experience, I don't know why. I was saying I really don't know the internal working of the OpenBSD kernel. But the mBuff remains a lot of time allocated in memory, so we got plenty of time to place the interruption vector in the same mBuff. We could reserve some memory or map some pages in unallocated pages and jump there. But in fact, that was not necessary. I was thinking, this is going to be a lot difficult. We must map some part of the memory, unused, but it was not necessary because it worked right away. Worked like, 90%, 99% of the times. So, but this is a nice, it's an excellent question. So we are hooking the interruption vector, and we must find if the process calling us is root, because we want to override, we want to take over a process that got root privileges. First, we find the current process variable. The current process variable is in fact something like an array, because OpenBSD is multiprocessor. Is placed in somewhere of the memory. It can change for kernel from kernel. Is placed in a static position of the memory. We must find it. How we find the current process variable? Well, we search for a pattern of memory. We are searching. We have a lot of kernel exploit using this technique, that is search for a pattern, because we can't do much else. We find a pattern that never changed in OpenBSD in like 10 years. We found a function that is an assembly function, never changed in 10 years, and we found exactly that pattern. We searched for that pattern and found it. We know that the current process variable is an offset from that pattern. So in this way, we found the current process variable. When we got the current process variable, we know a lot of info about the process that are calling us. We know that, for example, the user ID that owns the process. With the user ID, we know if the process is root or not. So we basically do it all by hand. Let's say we search in the memory, and what's happened if the user is root? Well, we must take over the process, because we now know that we got a process with all the privilege. So we must take down protection of the OpenBSD kernel. We must think, well, now we know that the process calling off is root. We can simply write in the return pointer. We know the return pointer of the interruption is in the stack. So we simply could overwrite this and make the kernel to return to our code in the user, in ring 3 and in user mode. But this is not good, because maybe the process, the function that are calling us is, let's say, libc, or an important library of the system. If we overwrite the binary that are calling us, we are breaking all the system. So we must jump. The best idea that occurred to us was to try to overwrite the stack, to try to execute code in the stack, because we know that the stack is one for every process, and if we overwrite the stack, we must leave all the other process alone. We must leave the other process will execute normally, and only the process that calling us will execute our code. Of course, we execute code in the stack is an old exploit technique, but OpenBSD had a lot of protection in user mode. So we must take down all the protection, because OpenBSD won't let us to execute code in the stack very easily. It got especially one protection that is called WSORX. This protection says or implements that every portion of memory that is writable is not executable. So it's exactly what we want to do. We want to write in the stack and execute it. So we must take down this protection. This is something easy to do if you are in kernel, because this protection is implemented messing with selectors. Basically, with selectors are used in the Pentium 32 bits, and they say where a portion of the memory is executable and where is not executable. We simply, OpenBSD system, just fix or let's say they place the selectors in a specific pattern, and to prohibit, to let the process stack to be not executable. So we can change the selector because we are in kernel mode. So we just simply extend these selectors. These selectors are let's say, they mark a very little portion of the memory as executable. In fact, they mark just the first part of the memory as executable. So we simply extend the selector, and the act of extending the code, specifically this selector, the code selector, simply makes all the memory executable, including the stack, the heap, everything. So the system now is like, I don't know, Windows 95, because we can execute in every place of the memory. Now that we can execute in every place of the memory, we simply put the code in the stack and modify the return address to point to our code in the stack, and that is the next time that the system call execute and then returns to the stack of the process, and then it executes our code. Then of course we must restore the original interruption pointer, because if not, this gonna take this pseudocode, this portion of code will take over all the root process of the system, and that is not a good thing to do. We must take over only one process. So when we are finished take over the process, we restore the original int80 vector, and the OpenBSD kernel is running normally forever, let's say. It works perfectly forever. But now, the root process that calling us is executing our code in the stack. And now we can execute in user mode. That is much easier to do it than in kernel mode. In user mode, we can write things to the hard disk, we can make an internet connection, we can do everything. So, what happens if the process is not root? If the process is not root, we didn't do anything. We just continue with the original system call. So this hook acts only when the first system call from a root process is made. And if the system call is not made from root process, we didn't do anything. So here now we got our code executing in the stack in user mode. We say, okay, we are finished. We won, but we not won. This exploit is a little complex. Why? Well, let's see. This is the drawing of how OpenBSD manage the memory in the Pentium 32 bits processor. like I was saying, this portion of the memory is executable, only the low portion of the memory, because the call segment only reaches from here to here, and here are placed all the executable portion of the process are the text section, and all the libraries are placed here. This is variable, it's not always 500 megabytes. The system moved this but the important thing is that the heap and the stack is always in the non-executable part of the memory, and using this code, extending the selectors, we made all the executable. We really don't need the heap to be executable, but we need the stack to be executable because we are placing our shell code, our IRC code here. We extend everything. It really don't need to extend this, but we extend it anyway because it's easy. It's easier. Here is the part of the code. I'm sorry, it's a little hard to see assembler at this time of the morning, but here is the part of the code that implements the pseudocode that I was explaining in the other transparency. They are using a little instructions that are not commonly seen in user mode. We got the local, in this instruction we got the descriptor table we find in the memory. Where is the descriptor table? In the descriptor table are the data about the selectors. Here is a little difficult to find because in the Pentium 32 bits the selectors are like are not placed in one place. We must like reconstruct them because they are placed in like mixed in the descriptor. In the descriptor, in every descriptor. No, sorry, not in every descriptor, but some of the descriptor got information about the selectors. We must reassemble the selector using this instruction. These only are shift and Boolean operations that assemble the selectors. And here, with these two instructions, we extend the selector. We just simply do this operation here. The code selector from here and extend it from all the memory, only with this OR. So we found where the descriptor table is in memory. We assemble the selector, and with this instruction, we extend both selectors here. This code works. You say, why I torturing you with this strange code? It's because this code is independent of the operative system. It works in every operative system because we didn't call anything here. Every operative system that implements a protection using selectors, modern operating system implement protection uses selectors and another characteristic of the Pentium. OpenBSD use a lot of other protection, but not in the Pentium 32 bits. In the Pentium 32 bits, it only uses selectors. That is because OpenBSD got this kind of protection even in very old processors. So, in this code, we just simply unprotect all the user space. This code works in everything. It should work in Linux and a lot of places. And, okay, we are executing code in the stack. But there is a catch. OpenBSD will not let us to execute code in the stack forever because in the next context switch, it will restore the selectors because the selectors are restored every context switch. So we must find a place on the memory to safely execute our code because we are running on time. In the next few milliseconds, OpenBSD will make a context switch and our code and will crash because the section of the memory that we were executing into will suddenly not be executable anymore. But there are two ways to do it, to find a portion of the memory that is executable. So Hey, come on. One of the procedures is to shut down WXORX from user mode. This can be made using a system call. Again, we are now in user mode, so we can't call any system call. We use a system call that is called mprotect. The system call is used to change the protection of the memory. It's totally legal to make a call to make this call. So we are executing the stack and make unprotect of the portion of the memory that we are into. So we unprotect. We unprotect the stack using this function call, and then of course we need to. We know we can't execute forever, but it will be nice that the process that we take over to continue to execute normally, because the process might be important, might be like I was saying, might be a web server process. We did not want the server to stop responding, so we must fork the process, and this system call we call the process of fork, and to make like a clone of the process. In one of the forked process, we continue to execute our shellcode, and in the other, the original process, we just fixed the return address. We know that the original return address, and the process continued to run perfectly. So we now have the process that we have taken over. It continued to execute normally, but we now got a forked process that is executing our shellcode, and is executing our shellcode in a region of memory that is unprotected forever. So the shellcode is executing here forever. There is another way to do it. This is the much easier way. We can call this mprotect in every place of the memory. We can unprotect the stack. It's a little weird, but we could do it. In fact, we didn't use this technique. We used this one. It's a little different. We just asked the operating system for a region of the memory that is always executable and writable. OpenBSD can do that, even if it has the WX or X protection. We can ask the operating system for a region of memory that it really didn't have the protection. So we just asked the operating system for a small portion of memory that got that privileges. We copy the shellcode from the stack from the stack to there. So we jump there, and we are not longer executing the stack. Of course, nice. So we are not executing the stack, and the process is running now in a safely place of the memory forever. Anyway, we must fork the same way, because if not, the process will break. So we choose this scenario to work. Here is a screenshot of the OpenBSD kernel. OpenBSD system, is a terminal. You can see there that the process has stopped here, has not crashed, but stopped because we placed a breakpoint in the shellcode. A breakpoint like it was in user mode. The OpenBSD system got a very nice debugger. It's called, DDB. And we can see here all the stack trace where the system has stopped. That if we continue to execute the kernel continues to execute perfectly. We stop it, and we quit executing. Okay, I'm gonna give a live demonstration if I can. Let's see, it's a little difficult. This can fail, of course, like every live demonstration. Let's see. Oh. I work in VMware. I'm gonna start OpenBSD virtual machine and send the exploit to Taskmaster virtual machine. I think I'm missing a form. There it is. I hope the resolution is not very big. Oh, right. Okay, you just keep running. And I'm going to send the attack from a Linux. This is exactly the same image that I used to send the exploit, to develop the exploit. Here is, you can see the little faster and everything. So, we're going to run. No, this is not. I don't see very well. I think this. From this virtual machine, we're going to send the attack to this another virtual machine. Okay, this is OpenBSD is checking this file system. So here is. We can see it. Here is the little fuzzer that I was using. It's made in Python. It's very primitive. Like you can see, I just put the byte together. This is the shellcode. This is the packet. And I put the byte together, byte from byte, and assemble the shellcode here. We can see that here is a CC code. This is an interruption tree in assembler. So theoretically, when the code will be executing this code, we will stop right here. Let's see if this happens. Let's see if OpenBSD is finished. Right. We'll just send the attack. Here are sending. And here we can see that the OpenBSD kernel has stopped exactly in the same time. It's not crashed, we can see. It just stopped. We can see using the debugger. Let's see how it was. Here. This is our shellcode. We can see there is a call, a pop, and an add. And here we got this instruction. This is a call, this is a pop, and this is an add. So we're seeing this part of the code exactly here. Oh, come on. Now the kernel is stopped. Every process is stopped, but it's not broken because if we give a continuum, we continue to execute perfectly. And now there is an invisible system called hook in this kernel. In fact, maybe if we leave this kernel working for an hour or two, this will crash because this is a very early version of the exploit that did not fix the MBUF buffers. But now we can see that our interruption hooked. If we place this system, this breakpoint in the hook, you can see here, because we place this breakpoint in the hook, it will stop every time a system call is made. Oh, I'm just trying to manage this thing. And of course here we will put a knob instruction. Now we have changed. Come on, save it. Oh, there it is. We must change the attack to stop in every. Where's the root? Oh, very good. Now we must fire a different attack on here. We must stop in the OpenBSD on every system call. Well, meanwhile, I can show you another interesting thing, another very interesting thing that was found. This thing. This was a very famous bug because it was the second. But there are, looking about in the patches, we can see that there is maybe a third remote vulnerability because we can see that the code here use this variable as an initialized variable. This is a simple patch that I was looking in the same way. I was looking for another vulnerability, and I found this little code here. Oh, sorry. That is an initialized variable fixed, like 3 months ago. This cause are first of all is a denial of service, but I think that is exploitable too by the right people, not me, but some very good people, I'm sure, that can exploit this. It's not very important because it was present on the trunk of the kernel only a couple of months. Nobody download this, but it's advice that is very important to keep an eye of every patch, and every bug can be exploitable. So it's not software. It's perfect. Like it was the ending phrase of this presentation. So well, I think I really didn't have any more time. So, but trust me that the live presentation that I was making is gonna work. If you want, I'm gonna show to any of you. Okay, that is all. This was one of the exploits. I would like to go to another. I think there is another presentation talking about the same exploit. It's made for the kernel wars guys, and I would like to see how they made exactly this exploit. I recommend you to go to that presentation. They are making kernel exploit from a long time. This is my first kernel exploit, and of course it's surely not very well, but it works. Trust me, it works. It's already on the client's machines. Okay, thank you very much.